Hi, this video is on the product rule and the quotient rule. Learning intentions are that you understand where these rules come from, what they are, two forms that they can be presented in, and an example of how we use them. Now, the product rule, what is it and what is it for? Well, this is two ways that we can write it down here. This one here is the one that's on the Maths Methods formula sheet, though this is an alternative one that I'm going to show you how to use, and is a bit kind of cleaner and simpler. Now, basically, what is it for? It enables us to differentiate functions that are made up of two functions multiplied together. So, for example, if we had something like 2 cos x e to the 3x, like that, for example, we have a function made up of two different functions in x multiplied together. This rule enables us to differentiate this function. Unfortunately, it's not as simple as just differentiating this, and then timesing the answer together. But it's not terribly complicated. So all you have to do is take one of the functions, multiply by the other differentiated, plus the other function times by the other one differentiated. We'll have a quick look at where it comes from. The product rule is an interesting one. Now, this in order to follow this, you really must remember differentiation from first principles. And although we usually use an h, I'm going to use an a for the small amount that is varying, because otherwise it's going to get confusing with another h that I'm using. So if we say that f of x, if we just remember, is some function, and then f dash of x is the limit as a approaches 0 of f of x plus a minus f of x all over a. And we'll come back and use this result in a minute. Now, what we're dealing with here is f of x being equal to two functions multiplied together. Let's call them g of x and h of x. So you can see why I didn't want to use h. So f of x is equal to g of x times h of x, which means that f dash of x is going to be the limit as a approaches 0 of this differentiated. So that's going to be g of x plus a, h of x plus a, minus, so I'm just using the same pattern here, g of x, h of x, like that, all over a. So far so good, but not terribly helpful. Now, what we can do next is a little bit of kind of mathematical sleight of hand. I'm going to add something and then subtract that same thing so that it doesn't actually change the value of this expression at all, but it does enable me to group the terms in an interesting way. So this is still the limit of, now what I'm going to do is, actually it's a different colour, add g of x times h of x plus a, and I'm then going to subtract that same thing, minus g of x times h of x plus a. And you might be thinking, well, now hang on a minute, why are you doing that? Adding something and then taking it away is surely not going to change anything at all. And you're right, it doesn't change the value of it, but it does help me group it in a different way, and I'll show you what I mean by that now. And that's all, there we go, divided by a. So what I can do now is put this term together with this term and this term together with this term. So what I end up with is g of x plus a, h of x plus a, minus g of x, h of x plus a. So I'm going to borrow that one, put it with this one, and I'll put the other one then, g of x times h of x plus a, minus g of x, h of x. Now you'll notice that all of this is divided by a, so I could split this up like this and just say, well, that's all over a and that's all over a, and I've got these two separate terms now. And what I'm going to do next is factorise. So I take g of x plus a, h of x plus a out of both of these. So I've got h of x plus a like that. That leaves me with g of x plus a. See that there? So I take that out. So g of x plus a minus g of x. Now, this whole thing's over a. It doesn't matter whether it's all over a or whether just that was over a or just that was over a. So I'm going to choose to write it as if it was just this over a. And over here we've got, I'm going to take g of x out as a common factor, leaving me with h of x plus a minus h of x. And again, I'll do the same thing, and I'll just choose to write the a just here. I could write it over the whole thing, but it doesn't matter, it's equivalent to the same thing. Now, I don't know if you can see what's going on here, but this here is, by definition, as a approaches 0, g dash of x. And this over here is, by definition, h dash of x. So what I've got as a approaches 0 is this, I'll come on to this in a second, multiplied by g dash of x plus g of x times h dash of x. And this thing here, you might not like this very much, but as a approaches 0, h of x plus a approaches h of x. So this is what I'm left with. F dash of x is equal to this, which is the rule that we had up before. Okay, there we go. Now, there's the thing we've just proved. F of x times g dash of x plus f dash of x times g of x. Another way to write it is like this, and I prefer this really because it just makes everything nicer and cleaner. If we have y equal to uv, then y dash or dy dx, if u and v are functions of x, is vu dash plus uv dash, and I like this because it spells vuv, which is nice and easy to remember. Okay, so if we have a look at the one we were doing before, the example we looked at before, if we want to differentiate 2 cos x times e to the 3x, we let u equal 2 cos x and v equal e to the 3x. Yes, we could let v be 2e to the 3x and u equal cos x if you like. It doesn't matter, the way the 2 goes doesn't really matter. So I've got two functions there, and then y dash or dy dx is vuv, which is v e to the 3x times u dash. 2 cos x is going to differentiate to give us negative 2 sine x, and then that is plus u, which is 2 cos x, times v dash, which is 3e to the 3x. And we can just tidy that up a little bit. That's going to give us negative 2 sine x e to the 3x plus 6 cos x e to the 3x. And you could then factorise, and that would give us, maybe take out 2e to the 3x times 3 cos x minus sine x. Okay, there we go. So we've differentiated that function. Nice and easy. You see the actual use of the rule is very, very straightforward and simple. Alright, now we've got the quotient rule. What is it and what is it for? Well, this enables us to differentiate functions that are of this form. So they are one function divided by another function. And this is the rule. This is the one that's in the maths methods formula sheet. It's quite messy. Again, this one, my preferred one, y equals u over v, then y dash is vu dash minus uv dash over v squared. No surprise, this also has vuv in it, which makes it nice and easy to remember. Now the proof is quite nice for this. All you need is the product rule and the chain rule in order to prove this. So if, for example, we know that y is equal to u over v, we can rewrite that as u v to the minus 1. Bring that up, that's as if it was v to the power of 1. So you bring it up and then we just use the product rule on it. But when we come to differentiate this part, we have to use the chain rule. So I'll just very quickly go through that, just for interest. So y dash is going to be, v is our v to the minus 1 times u dash plus, remember we're using the product rule to prove the quotient rule here, so plus u times, now when it's this bit here we have to differentiate v, and v is v to the minus 1, so we're actually going to get negative v to the minus 2 times v dash. That's using the chain rule there. Oops. And if we tidy that up, that gives us u dash over v there, so v to the minus 1. If I bring that down, it becomes v to the 1. Plus, actually it's not going to be plus, it's going to be minus because I've got a negative here. U v dash over, now when this goes down, I take it to the bottom of the fraction and it becomes v squared. It goes from a negative to a positive power down there. And I can't quite subtract those just yet, but I almost can. If I multiply top and bottom by v, I get v squared, so I can then just subtract that, and that gives me vu dash minus uv dash over v squared, which is the quotient rule. And there. Okay, so now using it, let's say y is equal to 2 cos x over e to the 3x. What we're going to do is let u equal 2 cos x and let v equal e to the 3x. We're going to use the rule dy dx, or y dash is vu dash minus uv dash all over v squared. It can help just to write everything out kind of together like this, keep it all nice and neat. 2 cos x differentiated is going to give us negative 2 sin x. V dash e to the 3x is differentiated, is going to be 3 e to the 3x. Then we can just pop them in. So we'll have vu dash e to the 3x times minus 2 sin x minus u, which is 2 cos x, times v dash, which is 3e to the 3x, all over v squared. Be careful when you do these, always use brackets to start off with. Now you'll see, even before I start to tidy these up, I've got e to the 3x here, e to the 3x here, e to the 3x here. That's going to cancel with one of those. So I'm left with negative 2 sin x, negative 6 cos x, all over e to the 3x. I'll probably leave it like that. I don't really need to tidy up too much more than that. Okay, now some things to look out for, things that look like products but aren't. So a common trap for people to fall into is thinking that this is a product rule, and it's not. It's cos of e to the 3x. So you got to be careful here. That's going to be a chain rule. It's a function of a function, not a function times a function. So dy dx or y dash would be negative sine of e to the 3x multiplied by this differentiated, 3e to the 3x. So it would be negative 3 sine e to the 3x e to the 3x, like that. You can rewrite quotients as products and use the product rule. Sometimes you have to use the chain rule as well. So if, for example, y was equal to sine x over e to the 2x, you could rewrite that as sine x times e to the minus 2x when you bring this up. Change the power. Then you could just differentiate it using the product rule. Let u equal sine x, let v equal e to the minus 2x. Another one where you would have to use the chain rule might be something like sine x over x plus 1 cubed, and in that case you would have, and you would use the chain rule on that part when you use the product rule. Okay,